in fact, let me go to the last class, the notes, which I still have not put up sort of deliberately. Yeah, so we started constrained optimization, and then we saw several examples, but we sort of left it a bit hanging. Specifically, this condition over here. I said that there is some condition that is required, which I did not specify. And in order to get to this condition, we started talking about tangent spaces, and then we just sort of ran out of time. So let me state the thing precisely. And and then we will see the proof to the extent that we can before going to inverse and implicit function theorem. So, all right. So recall the situation that I have. Okay, so you know what? Let me just instead of making a mess over here, let me just let's just say so this is the condition that I want to put. Okay, so let's first just understand what's going on, and let me start recording here.
Recording in progress.
Okay, so we have two C1 functions from an open set, real valued functions. One of these I think of as the objective function that I want to maximize or minimize. And the other one is the constraint. So I set this constraint equal to some number and take the corresponding level set m. Then the Lagrange multipliers method gives me a way to calculate candidates for this maximum or minimum by a certain recipe. So let's look at the recipe. And so let's see carefully what the assumptions over here are. The assumptions are both the functions f and h are C1 functions. And I'm assuming here that the derivative of the constraint function at the candidate is non-zero. So this is an interesting condition. We will explore the meaning of this. But this is the extra condition that I want to put. In this case, we are saying that at this candidate, what must happen is that the derivative of f and the derivative of h, one must be a scalar multiple of the other. And notice that because I have said that h prime is a non-zero operator, therefore f prime must, I can say that f prime is a scalar multiple of that rather than putting lambda on the other side, because nowhere am I saying that f prime should be non-zero, right? In fact, in the unconstrained case, we know that at a maximum or a minimum, at a critical point, at a maximum or a minimum, the derivative of f will be zero. So it is quite possible that lambda is zero. And we have seen an example last time, as I will just show you. So anyway, so is there any question about the meaning of this? So we can state this in terms of the derivatives of f and h, or equivalently in terms of the transposes, that is the gradient vectors. So the only thing that I've added to the recipe over here is that in order to apply this condition, in order to apply this recipe, I want to check that the derivative of the constraint at the candidate point B, where I have a local extremum, is non-zero. And if you can see if you see the examples, that is the case in all the examples that we saw. So because a square plus b square is 1 in this example, this gradient is not zero at any point, in fact. Let's look at the second example. In this case, remember h prime, the H prime has a component 1 in the second slot. So of course it is non-zero. See what happens in the third examples. In this, so this was an example that I wanted to show something, but I failed. But over here again, notice what has happened. The gradient of H has 1 in the second slot. Now let's do something a little bit different over here. I will, and you can see in the remaining examples also that the method applies because the gradient of H is non-zero. Now let's just see the modification over here. Let us suppose I take f of h of x comma y to be y square. What changes? Come on, this is not difficult. So I want y square to be 0. Now this is kind of an idiotic thing because y square being 0 is the same as y being 0. But if I just apply the recipe, then the gradient of h now is no longer 0, 1, but it is 0 and 2y. What does this give me?
So actually the lambda may be anything, but
Right.
h
So
will
you
be
see,
0.
right. So you see, the constraint actually does make sense. The constraint gives me that the point P has to be the origin, and which is true by the way, right? This function x square is going to have, I'm taking it only on the x-axis, and of course it is going to be minimum at the origin, so it works perfectly well. Then get xy equals 0, 0, but lambda is arbitrary. So you can say, well, the method, does it work? The statement as it is made here is false. There isn't a unique lambda. But the method works. However, it is quite possible. By the way, here is an example. The unmodified example 3. Notice that I got lambda equal to 0. So that is quite possible to get. Let me just say something more, which is that in absence of the condition h prime at P non-zero, so what does it mean that the method fails? That means that it can happen max at P where h prime of P equal to 0 and the method detect. So here's a simple example, and it's really a modification of the earlier example. By the way, I should really just sort of give also a ridiculous example. Okay, so let's look at the statement. Suppose the function h is the 0 function. It's perfectly valid, right? It's a C1 function. In that case, what is my level set? And let us say C is also 0. And h is the 0 function. What is the level set?
R2.
Or whatever. I mean, whatever is my open set U, it is the entire domain of the function. And it's an open set. So in this case, there is no constraint, in other words. And my earlier method tells me that if I have a C1 function and if I have a maximum or minimum, then the gradient of f has to be 0. Um, well, so in that case, what is the value of lambda? First, is the equation valid? And the answer is yes, because the left-hand side itself is 0. I know, and the right-hand side is also 0 because h prime is 0. So again, the value of lambda can be anything. So as stated, the theorem is false. This is kind of a more ridiculous example than this modified example three that I gave. But here's a more meaningful sort of counter example. And I hope that I get it right this time. So please check whether I'm right. So f of xy equals y. So it really is the same example. Okay, underlying example will be the same, but I'm just going to state it differently. Subject to the following constraint: h of x comma y equals y cube minus x to the 6, which is equal to 0. Okay, so this is a complicated way of saying something very simple. The constraint is that y cube equals x to the 6, but that really is saying that y is x square, right? Right, just by taking cube root. So in other words, y is equal to x square, but I do not want to put the constraint like that, because notice what happens over here. So clearly this function has a minimum. So what is so clearly at 0, 0, correct? And the value is also 0. But look what happens. What is the gradient of f?
0, 1.
0, 1. And so here's the question mark. Is this lambda times gradient of h? And what is that? Lambda times, what is the gradient of h?
Minus 6x power 5, 3y square.
5 and 3y square. And notice that there is just no go over here. This is not possible. Because the only way this is going to happen is when y square is equal to 1/3, right? Or rather, whatever, y square has to be something non-zero. Because you see, lambda times 3y square has to equal 1. But at the same time, 6x to the 5 is 0. So that means x has to be 0. But if x is 0, then y is also 0. Detected by the method. All right, so is this okay? So yes, go ahead, please.
No, sir, I said yes.
Yeah, okay, thanks. Okay, so now let's so this is what I want to do. So let us try to actually see a proof of so in other words, this h prime non-vanishing is a sufficient condition for the method to work. Sorry, that came out wrong. The silly example showed us that h prime non-vanishing is not a necessary condition. And separately, it is true that if that condition is not met, then it may the function may have constrained maxima or minima, but the method is not good enough to detect. Okay, so let's look at the proof of this, and then we will see that we will see sort of where this condition h prime of 0 is required, and we will sort of come up against the implicit function here. So let's do that. I'll just start new notes. Okay, so let's recall the definitions of So tangent space. So given an open set U in Rn, and this function today I'm going to call H, a real valued function. Let's take a C1 function. And let's say I have some, and then I take the level set H inverse of C. Let's take a point on this level set, and let's take this condition H prime of P not equal to 0. So this is the new condition that I'm putting over here. So then what was the definition? The tangent space to M at P is T sub P of M. And so these are all vectors that are in the kernel of this derivative operator. So V is in Rn such that H prime of P evaluated at V equal to 0, which is exactly the same thing as saying that the gradient of H at P dotted with V is equal to 0. Okay. And so what, since now we have, so the normal space, so this is NPM. This is just the things that are perpendicular to the tangent. All right. So let's write down the example from yesterday. So H is equal to y minus x square. And let us say C is equal to, what is it that we took it yesterday to be? A 0, doesn't really matter. And P is equal to, if I recall right, we took 3,9. In that case, H prime of at P is what? Come on, quickly.
Minus 6,1.
Minus 6,1. In other words, this is just, and TP of M is a subspace of R2 that is really exactly x comma y such that minus 6x plus 1y equal to 0. Line y equal to 6x. And the normal space is what line?
Y equal to minus 1 by 6x.
So let's draw this as a picture. So this is the point. And so the tangent space is okay. So let's start color coding over here. So the tangent, as we understand, is this line. But the line that we actually got was this one. So that's the dotted line. And the normal, as we understand, is this line. But the one that we got here is, okay, so now this is going to look kind of bad, but in that, okay. So I'm just going to say that this one is the dotted line, and this one is the red dotted line. So let's recall that we can make the geometric tangent space and the geometric normal space is you simply take these spaces and shift them by so that they could pass, they start going through the point. But remember that we should keep the memory of the point. So the way you actually do this is that you gather all of this data together and you make not a tangent space at any point, but a tangent bundle, where the tangent bundle is this following sort of collection. You have P comma the entire space, and you have this entire sort of set which is living not inside. See, the tangent space, formally speaking, is a subspace of R2 here, or in general of Rn. But the tangent bundle is going to be something that is a subset of Rn cross Rn, or rather U cross Rn, where U is the. So this is a way in which I can keep track of both the point at which I'm taking the tangents and the tangents themselves, like all of it put together in one package. That's why we call it a tangent bundle. Just a viewpoint, nothing more than that at this point. In differential geometry, what you will see is that this object itself can be given some kind of geometry. All right. So just definitions. So now do you see why this h prime of p not equal to 0, not being the 0 operator, it kind of makes sense to think of this tangent space as something intuitive. What if we don't put this restriction?
Kernel will be the whole space.
Yeah, the kernel will be the whole space. Whereas if I'm thinking of, so think of this as, a graph, somewhere or the other, a graph. And if I have one equation, then the graph of this is, this constraint, this level set is going to be something of codimension 1. That is, it will be an n-1 dimensional object. I would like to think of the tangent space to this as something that has the same dimension. So in R2, if I have the graph, a curve, then a tangent to this should be a line. Notice what happens. So example. An example where h prime of p is 0. Okay, so consider h of x equals x square minus y square, and c is equal to 0, and the point p is 0, 0. And maybe I should have asked you to come up with it. But notice what happens. In this case, what is the gradient? The gradient is just 2x comma minus 2y. But at the point 0, 0, so here the gradient is c. Right? And so the tangent space TP, I'll put quotation mark, is equal to all of R. So we should make sense of this geometrically rather than just this algebra. So what is going on over here? What is this level set?
So the level set is a single point.
No, this is x square minus y square.
Sorry. Yeah. So it will be the line, 2 lines.
Right. In fact, yeah, so that reminds me of doing something. So we should look at what happens when I take also x square plus y square. That's yet another thing that we will see. Okay. What is this going to be? The graph is going to be, so here m is equal to the two lines y equals plus or minus x. So the picture is this. Oops. Now do you see what has happened? So how many tangent directions are there at the origin? It's kind of weird, right? Because this curve has broken up into two parts, but the breaking up is not important. The point is at the origin, there is nothing that is tangential to all of it. But if I take different parts of the curve, then there are two different tangent lines. Namely, in this particular case, those lines themselves. But you can picture something where both of these are curved, like something like this. And even in this case, this might be connected, by the way. If I have some picture like this, then you see at the origin, I'm not going to have a good time in finding a tangent space, because the tangent space by its definition is a vector space. Remember, it is something that is the kernel of a linear operator. So it of course is going to be a vector space. In this case, what happens is that once I have two different directions, therefore all directions will come as linear combinations of those. You should try to find an example of this nature. Of course, what does it mean, try to find an example? I already drew a graph, right? But what I mean is, see if you can do this in terms of a nice formula. All right, so what happens if I take x square comma x square plus y square? Again, everything else the same.
So what will be the exact problem if the derivative is zero in the entire space?
There is no problem. I mean, the point is that I would like the tangent space to be. I can make the definition. There is nothing. See.
Oh, okay.
Right.
Okay.
It's just that, notice what is going to happen. Because this is a non-zero operator from Rn to R, it means that it is kernel. That means it's surjective. The image is going to be all of R. So the kernel is going to be one dimensionless. So this corresponds, this corresponds to my idea of what the tangents should be.
Okay.
What happens if I take x square plus y square? Again, C is 0. In that case, the graph is just a single point. Right? Because x square plus y square, for that to be 0, I am going to, because I am over real numbers, both x and y have to be 0. And in terms of the calculations, I will simply get 2x and 2y. And at the origin, both are 0. So again, the tangent space will be all of R2. Is this a wrong thing over here? Of course, what does it mean wrong? I mean, I made a definition and the definition is giving me something.
The curve is sort of intersecting itself.
But there is no curve, no? See, there is only one point here. So it's a zero-dimensional thing. So typically, so here is the idea of, so even over here, we can consider that this is a wrong thing. And what has happened is the following. You see, suppose I have even a curve in R3. Let's say I have a curve in R3. If I want to draw the tangent, something that is tangent to this at any point, what kind of object should that be? Should that be a line or should that be a plane, or what should it be?
Be a line.
It should be a line, correct? So the idea of tangents is local linearity. I want the best linear approximation. So what this means is that if my object has a certain dimension, then the thing that is approximating it linearly should also have the same dimensions. So if I got a point, then the tangent space, the tangent space should also be zero dimensional. And I'm not getting that. You see, the point of what is happening over here is that even though I have a single equation, my general idea is that if I put one constraint in a certain number of dimensions, then the dimension of the solution space should go down by one. And if I have over an algebraically closed field, then this does happen. But over real numbers, x square plus y square equal to 0 drops the dimension by 2. Anyway, but as far as our definition is concerned, we are restricting it to the case where the derivative operator is non-zero. And so we have our tangent space. All right, so this is okay. Let's now sort of, so where we are going towards is that I would like to understand justify this Lagrange multiplier. So the next ingredient over here that I'm going to consider is just a recollection, a recall. If I'm given, so I want to consider now paths in Rn. So what is a path? It's just let's say a C1 path in an open set in Rn for now is just from some small interval to U. And let us say if I want a path to be centered at P, then that would mean that 0 is going to the point P, centered at P. All right. So what is there to recall? The point is the following. If I have a function, and let me call this function to be g for now. I don't want to call it either f or h because whatever I'm going to say, I want to apply it to both of those functions. Is differentiable then I can just apply the chain rule, right? What do I get? So I have so first I do gamma, then I do g, and I calculate its derivative at 0. Well, what is that? I know exactly what it is. It's g prime of gamma of 0 times, that is in terms of composition or multiplication of matrices, times gamma prime of 0, correct? Which is equal to g prime of p times gamma prime of 0, or in in terms of the gradient, it is the dot product. Okay, all very well. So we call gamma prime 0 to be, maybe I should have said this earlier. Let's write this because this has nothing to do necessarily with G. For obvious reasons, we call gamma prime 0 velocity of gamma. And for obvious reasons, right? So what's the idea? Why do I call it the velocity? Well, imagine that this gamma is the position of a particle that is moving through space. Then its derivative is going to give me the velocity. Right? Okay. So in other words, this really is just the gradient times the velocity. So let me not write that, but I will just say it in words. So this is what the chain rule. Gives me. Now let's put the two things together. So I'm going to think of the tangent space. So I'm going to, okay, instead of babbling, let me just write down. So now this is what we consider. Consider paths on a level set M equal to H inverse of C. So in other words, path, or sometimes I may say curve also. All right. So this gamma is going to be a map from minus epsilon to M. So what happens? Something very, very simple happens. Then what do I have? So this H is a function, right? So remember that this is actually going into U, and I have a function H from here to R. So if I apply whatever that chain rule thing that I said, then what do I get? If I compose the function H, then this function is what? This function is C for all t in the domain of the path. What do I get therefore? A very simple thing comes out, you see. What do I get?
H dot gamma dash of
Yeah,
0 equals
but that is now equal to what?
0.
That's equal to 0, right? Because I'm just differentiating. See, both of these are identical functions, the left hand side and the right hand side. The right hand side is a constant function, so its derivative is going to be 0. So what this is telling me is that H prime of P multiplied by gamma prime of 0, as in product of row vector with column vector, if you will, or the dot product. What is this telling me? What happened with this velocity vector? Look at the two things. Now put the two things together. I saw that the velocity vector is perpendicular to the gradient at P. In other words, look at the definition of the tangent space. What did we find out? That if I take any curve on the level set, any differentiable curve on the level set, then the velocity vector of this curve, what can I say about it? It belongs to the okay, so maybe too many words coming, but really what this is saying is that the velocity vector is perpendicular to the gradient, right? But that precisely the defining condition of the tangent space. So what we have found by putting everything together is that velocity vectors of all paths gamma M centered at P. This is a subset of TP of Q. But now here comes sort of the main point, right? So key fact. In other words, in this case, what I have is that every tangent vector can be represented by a curve. And this is sort of a favorite geometric way of regarding tangent vectors, that a tangent vector is just going to be represented by a curve on the surface. In order to prove this, we are going to need implicit function theorem. So let me just say this. So proof uses proof of this fact
So I don't understand what you're saying here. What do you mean when h prime p is equal to 0, you have equality?
Oh, sorry. I'm so sorry. I'm so sorry. I'm so sorry. It's the exact opposite of what I wanted to say. When h prime of p is non-zero. See, that was the condition that I put in the Lagrange multiplier method, right? So in the definition of tangent space, it came, it sort of was a reasonable restriction to put for the tangent space to correspond in terms of dimension. Here it is coming up as a way that will allow us to represent any tangent vector as a velocity vector. Okay. And so this is what is going to use implicit function here. For now, let us just assume this fact and let us go ahead and finish the Lagrange multiplier. Okay. So now we do the form. So far in all of this, if you see, nowhere was the objective function used anywhere. I was looking only at the constraint. But now let's bring in the objective function. Now bring in f. Now, so let's apply. Now let's recall the objective function f, and recall that p is assumed to be a local max or min. Okay, very well. Let's take a look. If gamma is let's say a C1 curve on M, which is the level set, then notice f restricted to M has a maximum at P. In particular, if I look at f along any curve, still that point will be a local maximum, right? Then in particular, f restricted to image of gamma, that is, let me not write this, okay, image of gamma, that is the curve, also has is a C1 curve centered at P, or just passing through P zone. But what does that mean? That means that f not I. Therefore, what does it mean that restrict f to the image of gamma? That means that if I first do gamma and then if I do f, then what can I say about this function? Perhaps I should draw. Correct. So here, so let us say this is my M. Okay. This is the point P, and this is the curve gamma. Okay. Now f is some function, real valued function from here. All right. In fact, everything is, so here, the way I'm drawing this is that let us say U is 3-dimensional. So M is going to be 2-dimensional because I have introduced one constraint. So it's some kind of surface of which I have drawn some part over here. P is a point on that. And here this curve gamma I have written. So the point is that F composed with gamma is going to be a map from, so I have written gamma here, but it really is image of gamma. Since the function F has a maximum at P as a function on this surface itself, of course, restricted to the curve also, it is going to have a maximum or minimum. So by one variable calculus, I know that this function, this is going to be 0. At where? At 0. But I know what this is. This is exactly the gradient of F evaluated at by the exact same calculation times the velocity vector. So what did we find out? We found out is orthogonal to velocity vectors of all curves centered at all C1 curves. That's okay. And this is just a straight calculation. But the point is, this highlighted thing is telling me that under my hypothesis, all of these velocity vectors, when we put them together, they give me the entire tangent space. Now we are done. I claim that we are done. Why is that? Why? By claim, delta f of P is orthogonal to the entire tangent space. Sorry, I'm not using. But we already saw this is also perpendicular. You see, what is happening is for two very different reasons. Okay. The fact that the gradient of H is perpendicular to all the velocity vectors, that is just because H restricted to M is just constant. So in particular, restricted to any velocity, any curve, it is constant. So the reason for the second perpendicularity is very easy. The reason for the first perpendicularity is because at P, I'm supposed to have a constrained a maximum or minimum. So in particular, restricted to any curve on the surface, also it will be a maximum or minimum. But now why are we done? So this is an n-1 dimensional subspace of Rn. And I have two vectors that are perpendicular to this. What must happen therefore?
They must be on the same one-dimensional subspace.
Exactly. So they are, yeah. So they must be multiples of one another. But there is a reason why I put lambda on one side than the other. Of these, which one can I say is non-zero? By assumption, I can say that the gradient of H is non-zero. I have taken it to be non-zero. Therefore, the gradient of F may very well be zero, in which case the multiplier lambda will be zero. Right? And I know there exists unique lambda such that okay. So so this took more than I expected. So you see there are nice definitions over here. The definition of tangent space is very important. And the way of thinking about tangent space in terms of velocity vectors of paths is also very important. So these are nice ways of thinking. But the reasoning itself, after setting up these concepts, is very easy reasoning. We really didn't do anything difficult. Okay. So the interesting part in here is this idea that I can think of all tangent vectors in terms of curves. And for that, we will need the implicit function theorem. So what we will do is we are now simply going to set this aside, and we will prove the inverse and implicit function theorem. And then we will come back to this. When we come back to this, we will also do the case of multiple constraints. So next. Inverse and implicit function theorems. And come back to justify the claim. In fact, we'll then be able to prove the general version of Lagrange multipliers method, that is with multiple constraints. So okay, so let me state the multiple constraint version, and then you will see that it is not really difficult to guess. So in fact, let me do this as a way to try to get you to guess what the correct thing should be. So suppose, okay, so first thing is that f is an objective function, so it's going to be a real valued function. But now suppose I have multiple constraints. That is, I want to maximize or minimize f with respect to the constraint that h1 should be equal to some value c1. h2 is another function which I am requiring it to equal c2, and so on and so forth. So now instead of one constraint, I have multiple constraints. But this is okay. I can think of this as a single constraint, not just about not about a function that is real valued, but which takes values in as many dimensions as the number of constraints. So this is a sort of simple way of formulating it. All right, so how do I say this? So suppose f is open U in Rn, and H is the same open U in Rn. So in fact, let me not say open, same U. C1 functions. And let me write down and suppose C1 functions that M is equal to H inverse C for C in Rn. Now, earlier I had the suppose P in U gives a local max or min for F restricted to M. And so there is now supposed to be this condition on H prime of P, correct? That we had. So what was the condition when M was 1? Just the fact that this just the fact that this operator should be non-zero. But now in this case, this is not going to be a, just a row vector. It's going to be a rectangular, it's going to be a matrix. So what should be the condition on this? So this is one question mark. Then what did we have? We had that this was supposed to equal lambda times. So there exists unique lambda such that this was supposed to be lambda times the gradient of h. So clearly things have to change. How should they change? Any guesses?
Lambda is an RM and you dot it.
Correct. Exactly. So there exists unique lambda 1, lambda 2 up to lambda m, which are real numbers such that this is just so h is going to be h is equal to the function h1 to real value functions. It's a linear combination. Lambda 2 is the gradient h2 and so on. hm gradient of lambda m times gradient of hm at t. And the condition on h prime. So earlier, for the operator, in case of one constraint, all that I needed was the operator was non-zero. That ensured that. So okay, what happened over there? The point was that two vectors were orthogonal to the same n-1 dimensional subspace, right? In this case, you look at this level set M. What is its dimension going to be, or what should its dimension be? What do we expect it to be? So I put one constraint, the dimension drops by 1. Now I'm going to put M constraints in a space that is n dimensional.
N minus 1.
So it's going to be the difference between the two, right? And so this operator h prime, I would like it to, so I'll let you figure this out, but the idea is that here is h prime of p is by the way, this map is from where to where? R what to R what?
Rn to Rm.
Rn to Rn. Or if you want to say in terms of rank, the map h prime of p must have rank n. So we will come to this later. But for now, let's go to inverse function here. So what is the inverse function here? So let me just state it, and it may appear a bit complicated, but what it is saying is very, very basic and very fundamental. All right, so let's try to understand this. So what is given? I have an open set Rn, and from this I'm given a function. Let's call it f to Rn. Notice that the dimension of the source and the target, they're exactly the same. A C1 function. Okay. And let us say A in U under F goes to F of A, which I call to be B. Such that this all important thing F prime of A, which is a map from Rn to Rn, is a crucial condition. So this is what is given. Then I have the following. There exist open neighborhoods V containing A. Oh, sorry. This sentence is getting a little out of hand here. You see, there are two RNs, right? So I'm just saying this informally here, where the map is a bijection with a C1 inverse. So let me state this. Such that F restricted to V is a well, I don't need to say continuous because F is a image W, and all important, moreover, remember this is a bijection, right? So of course, set theoretically there is going to be an inverse. The inverse function from W to V is also C1. So full stop. So in terms of, so what I have is V, F, which is W, and this is F inverse. A is in here, B is in here. So this function is invertible. The fact that the inverse is also a C1 function tells me immediately what the derivative of it's going to be, right? So derivative of, derivative of F inverse can be easily calculated using what?
The chain rule.
Using the chain rule, exactly the way you have been doing in school, right? Using when you calculated the derivatives of log and arc sine and arc cosine. Okay, so this is a mouthful, but the idea of this function is, what it is saying is very simple and very important. What it is really saying is that locally, differential geometry is just linear algebra. Or in terms of, or another way to say this is that a submanifold, if I'm given a submanifold of a manifold, then in some local coordinates, I can just think of it as a linear subspace. So these things will not make sense now, but I want you to try to come to a place with enough thought and in a few days where you will learn to understand, where you will understand what this is saying. So I'm going to give you some references today, a math overflow discussion, which I want you to read over this weekend. Because tomorrow we should be able to, I think, finish the proof of this theorem. And over the weekend, I want you to really think about this. This is a very important homework that I want everyone to do. All right. So So any questions on the meaning of this? Okay, so now I'm going to ask you a question. We're sort of singing praises of this theorem, but you never saw anything like this in your first analysis course, right? Why?
So I think we did, but
Okay,
I guess it was just a much simpler statement because
correct. So that's the idea, right? I mean, since you didn't see it, I mean, this is supposed to be true for all n. So let's just check what it is saying for n equal to 1. All right. So what is this saying? I have some continuously differentiable function, and let's say on an open interval, a real valued function. And what is that thing saying about the f prime of a being invertible?
It's non-zero.
It's just a non-zero number. So at some point the derivative is non-zero. But notice the derivative is not only is the derivative non-zero at that point, f prime is supposed to be a C1 function. In particular, okay, so let us see what we are supposed to get. We are supposed to get some neighborhood of this point A and its image point B, such that the function is a bijection from one set to the other. Is this obvious? So I'm going to write this as a so remarks. No, so I don't really like the quality of this silence here.
So does it like follow from the Rolle's theorem?
Okay, all right. So how? So first I want to show that this function is in some neighborhood is a bijection, right? See, there are many things to say here. So in fact, let me write this down. Steps. Many things being said. So steps in proof. So I want to show that f is 1 to 1 in some neighborhood. So I may have to shrink the set smaller, right? It may not be 1 to 1 on U, but in some neighborhood contained in U. Okay. The moment it is 1 to 1, I can consider its inverse, but I need to understand what the image is like. So I have to see that I can construct those open sets the way we said. Construct open V containing A and open W contained in B, giving inverse bijections. Then I need to show that this inverse function is C1. But the C1 part is, so C1 has various things, right? First, it is differentiable and its derivatives are continuous. But the derivatives being continuous is okay, you see. If I'm able to calculate the derivative, I know what that derivative is. It has to be given by the chain rule. It's going to be the inverse of the derivative of f. And I know that the inverse of a matrix, if f as f prime as a matrix valued function is continuous, all the entries are continuous. But the inverse of a matrix is easy to calculate, right? All the entries, they are going to be polynomials in the entries of the original matrix. We are going to divide by the determinant. But the determinant is going to be non-zero because this f prime is supposed to be an invertible operator. It's going to be invertible at one point there, and by continuity, therefore it will be invertible in a neighborhood. You see, the determinant of this is non-zero and the derivative is a continuous function. So it will stay non-zero in some neighborhood, etc. So the C1 part of it is okay once I show that it is the inverse is a differentiable function. To show differentiability, we go into steps. We show that f inverse is continuous. it is differentiable. So those are the steps. So I want you to tell me what these steps are. We are almost out of time. But in the remaining whatever 2-3 minutes, can you tell me how these steps are going to go in the case n equal to 1? Okay, so let me sort of get you started over here a bit. So this derivative is non-zero, right? Let's say the derivative is some value alpha. F prime of A is some real number alpha, which is non-zero. In anticipation of the general case, we will do some normalization. You see, I can scale this function by alpha inverse. Constant, right? So if the original function satisfied whatever these properties, that is equivalent to this new function satisfying the properties. As you can see, I'm just scaling it by a constant. So, so that will allow me to assume that this f prime of A is actually 1. In one variable case, this is not really that important, but in general, this will be, the general case, it will be convenient to do so. Not essential, but convenient. Now, the derivative at this point A is 1, and the derivative is continuous at A. That means that in some neighborhood, A plus or minus epsilon, I can say that the values of the derivative are all going to be positive. Let's say 1 plus or minus half, correct? Or maybe I should say A plus or minus delta, because given an epsilon, I can find a delta, blah, 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 etc. Correct? So I can ensure that within this A plus or minus delta, the values of the derivative are going to be between half and 3 halves. This is nice for 2 reasons. Okay. One is sort of the straightforward thing. So what can you say about this function in the window from A minus delta to A plus delta?
It's continuous and increasing.
Yeah, so it's continuous, but I was already given that it is differentiable. But I know that the derivative at everywhere in this window is going to be between half and 3 halves. In particular, the derivative is positive. Therefore,
Should be like
yeah, sorry, say that again, please.
it's monotone.
Yeah, exactly. And in fact, in this one, it's going to be strictly increasing. Already 1-to-1 is all right. Okay, so and then you can also see that if I take an interval, this function is monotonically increasing, strictly increasing, in fact. So the image of this interval is also going to be an interval, etc. And then for the inverse, I have to actually show that the inverse is continuous, which you can think of, because we are running out of time. I'll leave this for you to do. Will this argument work in dimensions n to in general for n greater than 1 to show that that the function is 1-to-1?
We'll have to do some changing to interpret what increasing means.
Right. Yeah. So there are many different directions, right? So,
Sir, can we like take 2 points restricted to the line? So we need convexity.
right. Okay. So first of all, we can assume convexity, because see the neighborhoods that we are taking, we are allowed to take them to be however small, right? So I can always take it to be a ball if I want. So I may assume convexity. By the way, this thing that if the derivative is positive, the function is strictly increasing. What do we use for that? What is that based on?
Rolle's theorem.
Yeah. So essentially, I mean, Rolle's theorem, mean value theorem, right? So, and Rolle's theorem is sort of a stark way of saying this, right? In that, this can even tell us that without going through increasing, we can just show that the function is 1-to-1, because if the value at 2 points were the same, then somewhere in between the derivative would need to be 0. Is this available to us in the multivariable case? that the derivative is equal to
No,
something
we had
or
an
b.
upper bound.
Yeah, so we had an upper bound. So you see that use of mean value theorem is not really going to work just that way. Now this idea that if I can put line segments and use the mean value theorem in all directions, see if that works. Okay. Um, because I didn't think of it until our discussion. But there is sort of a standard way to do this, and that is to use a a sort of a very standard fixed point theorem, which is a contraction principle. And so we will see that tomorrow. But today, as an exercise, I just want to end with this. So for tomorrow, see the form. So so for a real number, I know that this is true, right? This is something that you learn in school and forever. Why is that? Well, the series on the right hand side, if I take partial sums, they form a Cauchy sequence. And so it converges, and what it converges has to be then work as the inverse of 1 minus x, correct? So analog of this for matrices. Well, what is the analog of 1 minus x here?
I minus a.
Equals exactly the same thing, right? So what is it going to be? I plus a square plus x. Right. So this is fairly easy. The argument is exactly the same. Why do I use the operator norm? By the way, is it important which norm I use to worry about Cauchy, etc., and
No,
no? Why is that not important?
because norms on finite dimensional vector space.
They're all equivalent, right? And so that means that if some sequence is Cauchy with respect to one norm, by the way, I think strictly speaking, we haven't defined Cauchy, but it really is the exact same definition, right? Just for the notion of size, you use the norm. So I can use any norm, because up to constant, it's all really the same. No? So if one things go, if you be anyway, so you can supply the words, but nonetheless, I want to use the operator norm here. Operator norm in this condition. Okay. Why do I need to use the operator norm here? Because the operator norm has a very nice property. When I start bounding things like a plus a plus a square, whatever, or a to the k plus a to the k plus 1, etc., right? I have to show that it's Cauchy, right? What is the crucial property of the operator norm that comes in handy?
A norm of a square is less than or equal to norm a.
Yeah, exactly. So you see, if I'm calculating the norm of, let's say, a to the 4 plus a to the 5 plus up to whatever, then by the triangle inequality, this is less than the norm of the sum of individual norms, that is norm of a to the 4 plus norm of a to the 5, etc. But from there to go to the geometric series and use this business about real numbers, I need to know that the norm of a square, how is that related to the square of the norm of a? And I have the correct inequality over there, that the norm of a square is less than or equal to the norm of a the whole square. So for that reason, the operator, it's important to use the operator norm. But being Cauchy with respect to one norm and another norm, it's the same. So please sort this out for tomorrow. And then we will use this very nice contraction mapping argument to show that, to get the one-to-one. But let's stop for today.
Recording stopped.
Yeah, okay. So I meant to ask one thing. So, okay, so we have less than half the people left, but are there any people here who have registered for the KVPY exam and would like to write it given an opportunity? All right, so I take it that the answer is no. If there is anybody like, if there is anybody like this in class that you know, you can ask them to get in touch with me. The point is that that exam conflicts with our analysis final. So I'm not really sure if anything can be done, but I would at least just like to talk to those people. Okay. All right. Okay, so I don't have anything more. So let me just also say one thing. Yeah, I'm just going to give you a few links that I found out. Okay, so I will now I will give these tomorrow, but this first math overflow question, you can see what it says. What is the implicit function theorem good for? There are many great answers to this, and you should really try to understand as many of them as possible. In particular, the one that I have given, the one that I have referred to. Then there is this great book that I have not seen, but maybe you can take a look at it. And if somebody sees it and finds something interesting, I would like to know. And finally, this our genius of this age, Terence Tao, he has a blog article on the inverse function theorem, which is a stronger version of the inverse function theorem than the one that we are going to prove. So if you get anything out of that, maybe you can let me know and I'd like to discuss. Okay, so I have nothing more. If there are no questions, then we can stop. And then on Friday, please come prepared. Try to look at the proof. It's a very, very nice proof. But if you come prepared, then maybe in class you can always for interesting proofs, at least for me, when I read them the first time, I don't really understand them. Sort of have to see them again and again to begin to appreciate exactly how the different parts fit together. The inverse function theorem and the implicit function theorem, they really are sort of cousins of each other. This is really one of the high points of the course, one of the handful of high points in the course. So it's worth understanding very well.
Sir, actually, sir, I said something about like taking 2 points and the straight line joining.
Right.
I don't think like it will work.
Okay, why is that?
Because we'll have to take the line to be passing through the point
Right.
that you're considering. So if you're taking two different lines, we cannot prove that it's one on those two lines.
Right. Correct. So you see, basically what you can do is that, let's say your derivative, you have shown, so by this adjustment, you have said that the derivative is the identity. This is a very small thing. It's exactly the same as what we did. So we can assume that the derivative is the identity function. Very well. That means that in some small neighborhood of the point of interest, I can assume that the derivative is going to be something close to identity. Okay. But you see, there are multiple problems. So does that mean that in every direction the derivative is going to be a positive number? You know, in some neighborhood, and okay, fine, maybe even that is okay. However, the point that you raised is the major issue over here. You can say that along any line this function is increasing, and therefore on that line it is 1 to 1. But how do I know that just the moment I step off this point A in one direction to some other point, let's say x1, and in another directions to some point x2, how do I compare x1 and x2? They're in two different directions. What completely? So how do I compare f of x1 and f of x2? Right? So I do have to grapple with this, and I will grapple with this again using the mean value theorem. But you see, the mean value theorem is going to give me only an inequality. And what kind of inequality does it give me? It really is the direction of the inequality that is required to appreciate what the difficulty is. So if I apply the mean value theorem to f, then the inequality is the norm of f of x1 minus f of x2 is
less than or equal to.
And that is bad for me, right? Because I want to really show that f of x1 minus f of x2 is not zero. Do you see? So the way it is stated is not going to be useful. I need to have something which allows me to say that f of x1 minus f of x2 is greater than or equal to something. Okay. And the point over here is the following. So technically, what you do is that you apply your mean value theorem not to the function f, but to the function f of x minus x. So this is sort of a nifty point that we will see tomorrow. But I think the idea is, and I didn't work this out yet, but so please think of this. I think the idea is going back to the one variable situation. You see, when I say that the derivative at a is 1, and in a small enough neighborhood, I am not just going to say that the derivative is positive. I'm going to say that the derivative is at least half. And that means that the function has to change at a certain minimum rate. Okay. And that means it has to move fast enough. It cannot have a slow rate. It cannot change slowly in that neighborhood. So somehow I think these two things are related, but the technical way of doing this is to consider the function not f, but f of x minus x. And then you will see that the triangle inequality, it works nicely. And I take a neighborhood in which the norm of the derivative is, I'm going to scale so that the derivative is it's scaled to be 1 at the point of interest. And then I restrict to a neighborhood by the continuity of the derivative at that point. I restrict to a neighborhood in which the norm of the derivative is at least 1/2. And then I apply the mean value theorem to the function f of x minus x, and then the triangle inequality works nicely, as we will see. I mean, essentially, I've sort of taken you almost all the way to now. It's just a matter of working.
Sir, I just have a general question.
Yes.
Will we be having a quiz anytime soon?
Yeah. So okay. So actually, I asked. So certainly not before the certainly not before the before like the towards the end of next week, because I will never say that, oh, we'll have a quiz in 2 or 3 days. I will not do that to you. But I asked you, and I forgot to follow up with you, is that I would like a time in the evening or basically outside class where we can have a relaxed time and you can write your quiz. So I haven't heard back from you about this. Ideally, I would like to do it maybe on a weekend. Are there any what is happening with your other courses, by the way? Is there a quiz slot or something like that was used?
For algebra, we used to have quizzes like on Tuesdays, 1 hour before class, and
Okay.
for APRG, we just had them in class.
Okay, but now I do not want to do I do not want to devote an entire class to the quiz. Okay, so Tuesday morning. Let's see what is possible. Maybe you can discuss among yourselves, and yeah, maybe we should try to have a quiz perhaps next weekend, not this coming weekend, but next weekend. So on Friday, please remind me to discuss this on Friday.
Okay, sir.
In general, I should also tell you, please relax about the quizzes, because in the quizzes, my idea is now we have done a fair bit of computational stuff. In the quizzes, I will ask you computational things. All right, so good. Let's stop for today.
Thank you, sir.
Thank you, sir.
Thank you, sir.
All right, so please do try to read this inverse function theorem. It really is a very nice thing.
Yes, sir. Thank you.